All right, we'll just make a start. So this is almost the last lecture. We have 1 week left. Going to talk about some GPU programming next time, but today, since we had some time to fit it in, I thought I'd talk a bit about sort of research software engineering techniques. So things we can do to make our code better quality. So hopefully today we'll go over sort of what skills am I actually referring to. So what are these sort of professional skills that we can benefit from? I want to give you guys some resources that you could go and like learn things on your own. But most importantly, at the end, I'll go through some examples of like how you can like develop your own packages and also contribute to open source. So like fix problems in other people's packages as well. That's a very important part about being a developer. So in terms of the software engineering skills, the 4 main ones that I want to talk about, it's not an exhaustive list, but the first one is version control. Hopefully, if you've been following along with a lot of the assignments, you'll have some familiarity with this. This is like Git and like using GitHub as well. Also testing as well with the assignments. All of them are marked by unit tests to make sure that your code is doing the correct thing, and this is done in like an automated way. We haven't spoken really at all about documentation, but we'll go into that a little bit today. But one skill that's not spoken about as much in like software engineering industries, but is very important in science, is reproducibility. So how do you consistently get the same results of your code and ensure that a year from now, if you need to rerun the same program, you'll be able to get the same answers out. A lot of you will have seen some form of version control before. So like back at school, when you're writing a report, you'll often have like 6 or 7 files that are all basically the same document at different stages in your development. This is kind of what people do naturally. I think with like cloud backups and things now, I hope people have stopped doing this as much. This has a lot of problems. And yeah, we don't like it here. There are better ways of doing things and better techniques. And so the main problem with doing this is you don't really know which one is the true version of your document. So it doesn't have to be a Word document. It could just be like your code or even your report if you're writing in like LaTeX. This is very prone to errors, and you don't really get much benefit by having these duplicate copies. I mean, how often have you gone back to old ones in the past? So we're going to sort of throw away this version of version control and move on to talking about the more professional way of going about this. And so one system that you can use for sort of tracking changes is Git, and Git is really good at tracking changes of text files, specifically text files. You can track changes of other things, but it's really designed for text files. So that's like your source code, like your documentation, and potentially even your like written papers if you're using like LaTeX as well. So I won't go too much into detail about how Git works, but just sort of cover the very basics. So in Git, you have this idea of like versions or states of your code, which we call branches. And you can think of a branch as like a timeline of events that tracks the state of your code as you develop it. And so all Git repositories will have a sort of a main state. This is called the main branch, which you want to regard as like your absolute state of truth. Like this is the true version of your software as you develop over time. So you can imagine taking like a snapshot of where that code is in time, and we call that a commit. A commit is like a snapshot of the state of your repository. So it's not just a single file, it's the state of every file in your repository. And just in case it's not clear, repository just means like the folder that stores your code. So often you'll start with a repository with just like a single commit on the main branch. And if you want to sort of make changes, you edit a few files, like add in a bit of functionality, maybe a few functions, and then you have to commit those changes to the main branch to sort of save them as the state. So now we have two versions of our software, one from the initial commit and one from the added functionality. So if you ever make a mistake, you have access to this entire timeline of information, and you can go back and forth between the different versions. And also, if you make any mistakes, you can easily undo them. So what Git does, it will track the changes between the states. It doesn't just like create an entire copy of your folder. It'll only track the differences. So it's very easy to undo the changes. You just click a button in most like Git tools. But we don't want to just develop on this main branch over time. It's not very sustainable. You could use it like this, especially if you're on your own, but it's not recommended. The recommended way of like writing this code is to create branches for developing a certain feature. So for example, if you have some code and you want to add like a user interface to it, you can branch from your main code and it creates like a copy of that timeline that's isolated from your main branch. And you can like create commits here to make sure that you're developing it in isolation, so that if you ever need to go back to your main branch for some reason while you're developing it, you can just switch the branch and you can keep like working on two things simultaneously, even if you're on your own. And so once you're actually finished like developing something, you can create a pull request, and this merges the changes back into the main branch. And the sort of main power of this, it doesn't seem like it's that useful at the moment, but if you want to, for example, create another branch at the same time, like add in some unit testing, you can branch these at the same point or different points in history. And these are all independent copies of your code, and you can develop them independently. So you can create two commits here independent of this UI addition pull request. The only difference is now the history. So added this first gray dot here has a different history to the main branch, and so they're like technically different versions of the code. And Git basically gives you some functionality to let you detect if you can automatically merge them together. So it's tracked all of your changes over time, and Git will work out whether you can automatically put the changes back in without breaking anything. The only thing that you have to worry about is if, for example, in both of your commits, you've changed like the README file and you've sort of added some text there, Git will detect that as a conflict, and you have to manually merge that together and choose which version from which branch you want to keep. And yeah, once you're finished, you can sort of merge it back in. The main reason we do this feature branching is so you can work with other people. So imagine you're writing a paper, and let's say Luke and I are writing a paper. I'll create a branch to start writing the introduction, but Luke's done a lot of the numerics and the results. So he has a branch to write his results. They're different parts of the file. They don't really touch each other, but we can work on it independently without us breaking each other's code, because they're separate, isolated copies of the code. So if I introduce some bug into the code that makes it not compile for Luke, he won't know that until we merge it together in the end, and that's when we sort it out. But until that point, he's free to work on his part of the paper. So just as a sort of differentiator, Git is like the software that tracks the versions of your code. GitHub is just a company that provides like cloud hosting for these things. There are other providers available. So we often call the sort of the true source of your code, like where it's hosted online, the origin. This is just the sort of the term that we use to refer to it. And so this is like the cloud backup of your code. And when you actually clone the repository and get a local copy on your laptop, this is your local repo. And essentially when we develop code, you'll hear the terms push and pull a lot. So if you make a commit on your side, you have the local version of your main branch and you make a commit there, it's now different from the origins version of the main branch. So you have to push your changes up to the origin to essentially synchronize them. So push, you go from your local laptop to the cloud. A pull is the opposite. So you take changes from the cloud and download them to your laptop or your computer. And this way of working sort of abstracts away a lot of details and lets you like effectively work with other people. So you can have your own copy of your code where no one will make changes that could break your side, and you can control when you synchronize back and forth with the origin. This is also really useful if you're developing on the HPC as well, because you want to write most of the code on your own machine and test as much of it as you can there. But you need to, at some point, transfer the code onto the HPC to be able to run. If you have it in a Git repository, instead of having to like manually copy over the files every time, you instead make sure that you've synchronized the copy with GitHub, and then from GitHub, you can pull down the local changes and it will handle all of the merges for you automatically. Yeah.
How easy is it to connect like the HPC to GitHub then?
It's fine. It's completely fine. If you use like VS Code to SSH into the HPC, VS Code handles a lot of the authentication stuff for you. So if it's like a private repository, it just gives you a link that opens a web browser to let you like sign in.
I guess you can only do it for like command line though, right? You can't.
If you're SSHing with VS Code, it has a source control like UI side, so you can use that as well, which is quite nice. Yeah, if you are using the HPC, it's probably good to learn a few Git commands, but all you really need is git fetch, which basically updates the state of what the origin is with the state of your local machine, and git pull to pull the new changes. And then if you are changing any code on the HPC, maybe you need to commit and push, but those are the only like big Git commands you actually will need. Good. So yeah, a few things on how to actually learn Git. It's a skill that you will have to practice, and it takes just time to get used to things. I know I just said about the command line, but my advice, if you're new, just avoid it completely. You don't need it for 90 to 95% of everything you will use Git with. So the alternative is to use like a Git GUI tool, which gives you like nice buttons for doing simple things. It also restricts your options. So instead of like asking something on Stack Overflow and getting some sort of magic commands that you don't really know what they do, you're sort of restricted in your options just to do the basic commands. And those basic commands are probably all you actually need. So yeah, the two that I recommend is GitHub Desktop. It's just an app you can download, but if you are on Linux, you can get GitHub Desktop, but it's a slightly different version. But there's also Git Kraken as well, which is practically the same thing. Also, if you want to just use the same thing everywhere, regardless of whether you're on the HPC or your local machine, there are plugins for VS Code as well that give you a lot of Git tools, which can be very helpful as well. So yeah, pretty much any guide you follow online, as long as it's like not tailored specifically to the command line, will be enough to learn the basics. But the main thing is to just practice it. So even if you're working on your own in your projects, just upload your projects to GitHub and just try committing and saving every so often. That's the sort of best way, is just experience. And in particular, try using it to write your next paper as well. So it integrates with Overleaf if you're writing your papers there. This is specifically with people writing in LaTeX as well. VS Code also has pretty good support for writing papers as well. Quite like Overleaf, it's a bit more setup, but it works better with Git than Overleaf does. Okay. So, any questions on the Git side of things?
Git with Overleaf, I assume you just type the paper on your local machine and get pushed.
No, so it has like an integration with GitHub in particular, so you can like give it the location of your GitHub repository and you can like commit directly from Overleaf your changes onto GitHub and sync with them.
Still typing the overleaf.
Yeah.
And automatically.
You still have to like manually do your commits and things, but yeah, it's pretty seamless. The main limitation, this may have changed, but the main limitation is you can only commit to the main branch, which is usually considered a bad practice. Yeah, that's it.
I think it's still like that. At least it was a couple of weeks ago.
Yeah, I think it is still like that. So that's why I tend to use the VS Code version instead, but it's up to you.
Sorry, so when you write in this overleaf, you just save the file, then you give me I mean, within this process, when should I commit?
So let's say you've finished writing like the introduction.
No, I'm currently in the
Overleaf.
Online version of Overleaf.
Yeah. So you're currently in Overleaf. You finished writing your introduction. Git will track your changes and basically be like, you've added these lines corresponding to the introduction or changed these sentences. And then I think it has a menu or a button that you just click and it will basically commit everything, all of your changes all at once. So usually with Git, you select which files and even what lines you want to commit. But
so this button is in Overleaf.
Yeah, it's just a big button to like click commit. And then there's probably a button to like sync and pull as well. But it's helpful if you're writing with co-authors and they're using their own way of writing their papers and you're using Overleaf. If you have Git, it's like a central way of communicating instead of like zipping up the folder and sending it to someone.
Everything gonna mess up very quick, right? Very soon, if there's only one branch. You mentioned there's only one branch for it.
Yeah, there is only one branch. I mean, if someone else is using something else, they can use a different branch, but as long as you're working on like different parts of the paper at the same time,
in this case,
you should be okay. And if you do get a merge conflict, like maybe you have to sort it out. I think there's a merge conflict resolver on GitHub, so you literally choose like which lines you want to keep, or you can do that locally as well. But it's easier to cross that bridge when it occurs instead of learning it to begin with. Yeah, that good? Great. I'm only going to talk a little bit about documentation here and just give you some examples and a book that is good to read on the topic. So this might be counterintuitive. So when you learn your programming, especially in the sciences, everyone always tells you just comment every single line, make it very understandable. Please don't do this instead. So usually, like comments are just making up for badly written code or badly named code. So in particular here, this function is called d a of b. You have no idea what d is, like it really depends. You only know that d is calculating the distance between something because of the comment in the string or the doc string above. Especially here, also the variable names have been shortened to save like 1 or 2 letters here and there. And the comments are saying exactly what the code says as well. So you're not getting any extra information other than just more vertical space on your screen. So the main point is most of the time when you have comments like this, they're pretty redundant. You can usually do without them. Try to make your code as expressive as possible by using good variable names. Yeah, so the main problem with this is the variable names just aren't descriptive. So it's harder to actually track what's going on. And yeah,
Questions in the chat. How do we as scientists move on from this kind of unstyled ragtag code to learning proper practice? This kind of thing you would learn on a comp sci degree. Will that just come with time and practice and reading style guides?
Yes, that's a really good question. So style guides are really good. So most languages will have some usually accepted style guide that's good to read. So that's like, how do you name variables? For example, do you do like Pascal case, camel case, snake case? Like, it's just like, how do you write the functions? If you if you follow these style guides, it makes it easier for other developers in that language to read your code because you have a common set of shared practices that lets you just read code a lot quicker. So a good example in Julia is using the exclamation mark on the end of a function to say that you're mutating the function. That's just a style guide. You don't have to do that. It doesn't change any functionality, but if you do that, it makes your code easier to use by other people.
By that being mutated, you mean you normally have a function which has the same name and this just does something, or it's actually like changing?
Yeah, I guess it like indicates from the place where you're calling it that your actually like the variable that you pass in will change in memory. So for example, if you're writing like the sum function and you're summing some array and you're summing like over the second dimension, this won't affect A. So A is completely unaffected and you can use it afterwards. But if you use the in-place version, it will reuse this memory instead of allocating a new array. And so if you expect A to be unchanged here, then your code is wrong, it breaks. So yeah, it's just a convention to indicate that this memory will change. And also, if you don't want to allocate memory, you usually look for the in-place version of the function, if it exists. Okay, so read out part of that question again, the one about the style guide. How do we learn it?
How is this the kind of thing you would learn? Oh, sorry, this is the kind of thing you'd learn on a comp sci degree, or would this just come with time and practice and reading style guides?
Yeah, it takes a lot of time. It's really
I guess it's also based on what company you work for.
Exactly, yeah. Many companies have many different styles. Everyone is very opinionated on this.
Within 1 week or 2 week internship, you will know, essentially.
Exactly. It's really hard to judge this. My main advice is, it is hard. You will make mistakes. Code that you wrote last week, you'll probably think is very bad, even if you thought it was good at the time. That just means you're making progress, so that's fine. In terms of like learning these things, I'll come back to this afterwards. But I have a book recommendation that's pretty good. It is like a few, like 2 decades old almost now, but it's still very good and it's actually quite an entertaining read. So I'll come to that on this slide, on the next slides. Okay, so we had the function on the previous slide. It took up like what, 10 lines of code. This, I would say or argue, is actually better. So here, we've changed the function name to distance instead of d. Distance is much more readable. We've changed the input parameters to say these are some type of vector. And so that adds some information as well, especially if you're not actually looking at the source code here. You're just calling this function. You'll be able to see when you're calling it what the argument types are. It'll show up in your editor. Also, the docstring now specifically says what type of distance, because there are lots of ways to calculate distances between 2 points. This is specifically the Euclidean distance. And I would argue this is better than writing the function called Euclidean distance, because that's too long. It will take up a lot of space in your code and make it harder to focus on the actual logic instead. So yeah, the other thing is when you're using like standard maths things that are used all the time, you don't really need to like fully explain it. Like most people know what Pythagoras is, and this is similar enough to the actual maths that you can get away with just writing it out as a function. If it is complicated maths, it's usually best in the docstring to leave a link to like see more information at this source. Also about maths as well, it's usually best to have good expressive variable names sort of like in the API of your function. So the arguments that are passed into your function should be named in a standard way, or at least fitting with the convention. Inside your function, you can just rename those variables to be able to write out the formulas in a way that's makes sense from a mathematical point of view. So instead of having these huge formulas with huge variable names, you can replace it with X or Y as long as it's named X or Y earlier in the function. And you have a good variable name coming in from the function arguments. Okay, so we'll have a look at this example. This is just a function that fits a linear curve to a set of X and Y points. And what gets returned from this is just like a tuple of the gradient and the y-intercept as well. Can anyone point out some issues with this code? Just like any issues at all?
The name in the doc string, or maybe the name of the function, they don't match.
Yeah, that's one thing. So this function is called linear fit, yet the doc string says it's called fit. That is an issue. Anything else?
He didn't specify the data type X and Y.
Yeah, so yeah, we didn't even specify what types they are. In Julia, the types won't affect the usage, but X and Y make it sound like it's a singular value, right? It's just one X and one Y, but what we actually want are arrays. So a lot of the time, if you have a variable that's a collection, you should probably call it X's or Y's with an S on the end to make it clear that it's plural in some way. I'd say the inside of the function isn't that bad. Like, it's fine. Like, no one's going to judge you for writing code like this. The reason why you have this denominator variable is just for like performance wise. You don't want to have to recalculate the same denominator twice. I would say having like variable names like M and C should be discouraged. Like, generally try to avoid like single letter variable names apart from the standard. So like N, for example, for the number of points in an array is pretty standard. That's fair enough. Using I, J, K for loop indices as well is also very standard. But the only reason that that's acceptable usually is because it's by convention. People are used to it as well. So usually the sort of metric you want to aim for is like being able to sort of read a function with the least amount of like mental effort possible. That's the thing that you want to aim for. You want other people to be able to very quickly understand what your code does.
So Julia allows Unicode / latex names, i.e. X squared. Is it bad practice to actually use these?
Yeah. So for those of you who don't know, Julia allows like Unicode. So for example, if you want a function that's like the derivative of f, you can directly put in like nabla into your code and name your variables with Greek symbols. I would say in math cases where the symbols are like very well understood in the domain and it's very clear what they're used for, it's fine. Use your Unicode symbols. To be honest, it makes the code more readable, specifically in a maths context. The only thing that I would caution against is sometimes Unicode doesn't play well with like the HPC, for example. So if you're trying to edit files or like run something interactively on the HPC and all your variables are in Unicode, sometimes the terminal can't display Unicode. So you just can't run code there. So there are some drawbacks, but it's a minor thing. I'd say don't go over the top. Use it where it makes sense. Okay, so this function, we can do a few things to make it better. It won't be perfect, but for example, instead of having this MC tuple get returned because the caller of the function has to basically keep track of like what is M, is it the gradient, is it the intercept, and like how to actually use these variables. So instead you can create a struct that will basically name these variables. So if you get back one of these models and you say like the linear fit gives you one of these linear models, you can say result.slope, and that's very informative. It tells you exactly what's going on, the type of the variable, tells you exactly how you expect the function to behave. And also you can use it in like functions later on. Instead of having to sort of manually write out the function for the equation of the line, you can just directly use your struct. The only problem is this is pretty easy to change. You just return the linear model instead of the tuple. You just pass in the M and the C values. Anyone spot the major issue that's remaining here?
I have a question with this first line.
Yeah.
You define a type called abstract model.
And then it doesn't do anything.
Yeah,
that is a problem. So the struct should inherit from or be a subtype of this abstract model. That's a mistake that I need to correct in the book.
Okay.
From the chat, and the struct is undocumented.
Yeah, so the struct is undocumented, but it has good variable names for slope and intercept, so it makes sense as to see like what's happening, and also predicts kind of makes sense as well. Like you have a linear model, you have an input X, you're predicting something from there. Maybe it could be better. The major problem is this docstring says that this function returns a tuple, M and C. It doesn't say that it returns the linear model. And so we've changed the function of our code. Like this happens all the time. People refactor, people change things, but they often overlook comments because as long as your code runs, like people don't pay as much attention to the comments. So that's the major reason why you actually don't want to include comments as much in your code. You want to make the code as expressive as possible, is because comments lie. They get changed over time, or they don't get updated when the code gets updated. So one thing that's really nice in sort of these modern systems that sort of test the quality of your code is you can add an example to the docstring to say, this is how you use this function. And this is what, like with these inputs, this is the value that will get returned. This is very helpful. You can access this in the REPL. We make use of this quite a lot with a lot of the inbuilt functions. What's quite nice is if you wrap it in this JL doc test environment, your sort of tools that you can create, like these web pages with your documentation, which we'll see later, can actually run these as unit tests and check to see if I do run these functions with these inputs, do I get a tuple of 3 and -7 out? And if it doesn't do that, then you'll get an automated flag saying, hey, this unit test doesn't work. So you'll see this a lot in packages, like packages that you use. They'll have a lot of these doc tests to make sure that the documentation for their code is synced up with what the code is actually doing. So just as an overview, this is the book I recommend. It's called Clean Code. It's by Robert Martin. He's very well known in the software engineering community. It's very opinionated, but this book is more entertaining to read than you would think. You don't think it's a very interesting topic, but he makes it a lot more interesting. Just as some sort of overview, focus your sort of documentation efforts on the functions that you expect people will use, even yourself will use. So if you have a load of library functions that do very small things, but you very rarely actually call that code, it's only called by other library functions, perhaps they don't need as much documentation, and they might even change over time. So it might not be worth investing that effort. You want to do it for the big functions that you use in your scripts on the front. Yes, and if you do want to use comments, just try to use them to describe the why of why you're doing the code a certain way if it's not obvious, instead of saying just what the code is doing. Because if it's not clear what the code is doing, you probably need to redesign it in some way. And just make sure the comments get updated when you update your code as well. It's really easy to miss them. Okay. Cool. So very briefly on unit testing, thankfully, all of you will have had exposure to this already. So in a nutshell, what unit testing is just writing code that tests your code. That's it in a nutshell. So you have some functions and you know how they should act. You know what they should be doing. And so what you can do is you can write code that takes your library code with some known inputs and tests it against known outputs, and you want to see whether it's actually doing what you think it's doing. These unit tests are usually pretty small as well. Like you should only like test like 1 or 2 functions at the same time. They're quite important in Julia as well, because you might write a bunch of code and not realize there's a load of syntax errors, and you'll only get the error once you run it and it gets to a certain point, and then you get an error. If you have some unit tests, you can catch these quite early as well, which is quite nice. So the main reason is, as soon as you have these tests, it's automated. It's very easy to run them again and again. So if you have, if you make a big change to your code, for example, and you optimize a function, you might not realize that you've introduced a bug where it actually makes a mistake. And the unit test could catch that. So instead of having to manually test every single input and output and see whether it's working correctly, if you have a unit test, it makes that process much easier. So yeah, you've seen this type of thing before. You just type in tests as package manager and it will detect all of the unit tests you have and run them. And you want to make sure everything passes. A few key things here is you don't have to unit test every single function in your code. Try to unit test the sort of outwards API of your code. So like the main functions that are like the entry point to your library. You could, if you want to be a bit more extreme, try test-driven development. So this is what you've been doing already for your assignments. I've written some tests and some functions that fail because they're not implemented. But you have the test there, and what you do is you implement the test until it passes. And so the main sort of ethos of test-driven development is red, green, refactor. So red, your tests fail. Green, your tests pass, and then you refactor your code to make it higher quality, but you still want your tests to pass. A lot of this can be integrated into CI pipelines. CI is continuous integration to make sure that these tests get run regularly on your code, to make sure you don't introduce bugs and only find out like a month down the line. Yeah, and there's something called code coverage as well, which basically will test how much of your code is being hit by a unit test of some form. And this is a sort of good proxy to know how well tested a library is. If it has a very high code coverage, it's probably quite a high quality library and probably has very few bugs, and it's quite robust to use. Okay. I don't think we'll get through everything today, so I'll be somewhat quick here. So when I talk about reproducibility, I mean being able to consistently run some code to get some results. And this also means being able to give your code to someone else and have them run your code and get the same results. So something you see quite a lot in functions is people write absolute paths to like their data sets or their files. So like which drive it's on, which folder, the entire root. Again, please don't do this. So almost every programming language will have some module or package that lets you do relative pathing in some way. And it's always better to use these libraries to basically work out what the path should be instead of writing the absolute path down. Because as soon as you run the left-hand side on someone else's computer, they're not going to have that file in that location. It's just going to break. So try to avoid it if possible. So one way in which I like to do it, I know this is Python, not Julia, but is just an example, is you can get the path like relative to the source code file, which is unlikely to change. And so you can use that to get the relative path to like a data directory that you know is going to be in a certain place. And you can use these joins to make sure the path is formatted correctly. This is really important, especially if you have like a Windows computer and then you're running your code on Linux. Because on Windows, you separate your path with 2 backslashes or a backslash usually. It says 2 here because that's just an escaped backslash. But on Linux, it's a / as well. So you've got to make sure that you're using the right path joiner as well. That's why you'll see people using this os.path.join, because depending on whether you're on Linux or Windows, it will use the correct separator for you. There's an equivalent of this in Julia. Like these are very standard across all languages. Main thing which we've spoken about a little bit as well is make sure you always use an environment that keeps track of which packages you're using as well. So someone else that gets your code, they can just instantiate your project, which downloads all the dependencies, and then they can just run straight away. You don't have to spend loads of time and develop a huge README for creating these packages, for like installing all of the dependencies and all of the setup. Yeah, I guess the main point from this as well is if you have loads of packages in your global environment, if you activate an environment, those packages carry on to your like project environments as well. So try to keep that as a minimum, because you might be using a package and it works fine on your system because you have, let's say, benchmark tools in your global environment, but it's not in your project environment. So when someone else goes to load it, the code fails and it doesn't run because they don't have this package installed. There are other reasons for keeping your global environment as clean as possible, but we won't get into that here. A final thing specifically for coding is it's important to think about random number generations, because these play a huge part in a lot of the research, especially the research we do in condensed matter theory. So most random numbers that you'll generate on a computer are generated in a pseudo-random fashion, which means it has some state, and every time you generate a random number, it mutates the state in some way and outputs a random number. But if you give the random number generator the same state, it will produce the same outputs in the same order. So it's basically entirely deterministic. We can use them as real random numbers because the distributions of those numbers sort of match real random numbers as well. So you can see here on the example on the right, if you seed the random number generator, which basically means starting it in a certain state, and you sum up and generate some random numbers, you do that twice, you'll get different results each time. But if you reseed the random number generator and reset it to a state and run it again, you'll get the exact same numbers as you did before. So if you have like a simulation and you want exactly the same thing, but you are relying on random numbers, seeding it is one good way of going about this. It's also really good for debugging as well. If you have an error that only occurs sometimes in your code, if you seed it, that error will happen in the same place, and you can really sort of work out what's gone wrong. Yeah.
You see, like the majority of like random numbers on PCs are pseudo-random, like any that aren't. That actually
yeah, I think
random.
you can get like extra devices that you can like plug into like the PCI port that helps generate like actual random numbers. And there are some companies that offer services of generating like actual random numbers. So I think there's a company that has like a huge wall that's just like a lava lamp, like a big chaotic system, and then they have like a camera looking at this system, and they use that to calculate random numbers. So they can't be predicted in some ways. Yeah, random numbers are really important. They're important for like cryptography and all of the science that we do here. So yeah, it's a big field of research, and yeah, something to look into if you're actually interested in that.
Apparently it's called Cloudflare from the chat.
Oh, there you go. Okay, so we don't have too much time, so I'll pick one of these topics to go over. Hopefully all of you will have heard about open source development before. So essentially people put their software projects out in the open and you can view their source code. But you can also contribute to it and like change things. So basically one way in which you can do open source or you can contribute to open source and make projects better is by giving feedback to the developers. Like this is the easiest way of happening. So if you use a package that has, and you find a bug or you have a feature that you want, you can go to their page, like on GitHub, and there's a whole section called issues, and it will let you, you can create an issue there, even if it's not your own repository. A lot of them will have these, I'll make it a bit bigger, these sort of guided issues to tell you exactly what information you should put there. So for example, here it says, this is where you put this, and we also want this information as well to submit your bug report. You write it here, and that will notify the developers about this. And then usually, depending on the project, they'll see this as a bug and give you some feedback, ask for more information. Or if they know how to fix it, they will see this issue, create a branch, do a pull request, and actually fix it, like on, I say on the spot, like within a week or so. So that's one way of doing things. It's like you're not actually writing code for them, but you're giving them a lot of useful information. If you actually want to implement it yourself and like extend some features, or you've noticed their documentation is lacking and you just want to add to their documentation, you can actually contribute code directly to their repository as well, even if you don't own this. So thankfully, Luke has said it's okay to use his repository as an example. So if this is on Luke's project, I can't clone this repository and I can clone it and like make changes myself. But if I try to push, it won't let me because Luke owns this. I can't just change his projects. But what I can do is create a fork of the project, which is like a copy that I own myself. And you can do that to be able to actually make changes locally and push to the cloud. And once it's in the cloud in GitHub, you can then make a pull request from your forked version of the repository over to Luke's original version. And then he has control of whether to merge those changes in or not. So as an example, when you go to one of these public pages, if you want to make a change, you can click this button in the top right called fork. And so this will go into your own repository and you can give it a name. I'll keep the main one. So now this is in my repository. Because this is forked, it gives you a nice button to help keep you up to date with what Luke's done. So if he's done a bunch of development and you want those changes in your fork, you can click that button and it will sync it back. So the way we're actually going to develop this is we can clone his repository. You can do this any way you want on your machine. And go inside, and I'm just going to open VS Code inside of the repository. So from here, let's say what we actually wanted to do is add like a README, for example. So you can add a README and say this is the kinetic Monte Carlo package. Let's say you actually fill it out and do something that's actually worth contributing. But once you've actually done this and you want it back in Luke's repository and you want him to see the changes, what you should probably do is create a branch for your feature. So you can create a branch, call it add README, and then commit your change to this branch. As I am on this machine, I have to commit from the terminal. Okay, so once you've committed, you can push up to the main. Yeah. So if we go back to GitHub itself, you can see that we have a branch here called add README. And GitHub is nice enough to know that you might want to create a pull request. So we'll follow that button. Now, because it's forked, you'll get some extra options here. So instead of merging in your changes to your forked copy, your local branch, you can actually create the pull request to merge into Luke's original repository, into main. And so if you were to create a feature, if you were to create an issue first, detailing the problem, and then implement it, you would, in the description, write what, like reference that issue and say that this is the pull request that fixes it. So if I create this pull request, you can see that this is actually created in Luke's repository. So he can see this pull request and he has control over it. And I usually won't get this option, but I am a contributor to his repository. So usually you don't see this on other people's, on other projects that you don't have ownership over. You don't have this button. But Luke will have access to that button and he can go through the changes, ask you to make revisions, and in which case you just do more commits on your side and just push the branch up and it will update the pull request. But yeah, from his end, if he's happy with your changes, he can just click that merge button and now your changes are in his repository. Have you accepted it or no? No, so yeah, so Luke didn't like my changes, so he closed the repository, closed the pull request as well. So I would really recommend trying this for very simple things. So if you're reading some documentation and you notice a spelling error, it's a really good chance to actually practice doing this, like forking the repository, finding where the spelling mistake is in their documentation, fixing it, and making the pull request. It's got merged in now. Thank you. Yeah, we don't have time to go through the creating a package, but I'll just show the resources for this. So if you actually want to create a package and like share it with other people, Julia makes this really easy. There are some packages that make it very easy for you to bundle up your code in a way that other people can use and add documentation, unit tests, everything. It's just a matter of like selecting options. So there's a talk by someone very active in the Julia community called Chris Rakorkus, and he basically goes through this entire process, developing open source and creating your package. And the main thing you want to use is PKG templates will give you the scaffolding of your project, and you can just copy and paste your existing source code in and make it work. So as an example, I'll open this. I'll open this here. So one package that I made lets you sort of run experiments on the HPC and save it in a database. But using this PKG templates, it's very easy to generate a documentation page. And you can write these docs in Markdown, which is like a very, very simple sort of language for typesetting. And you can write entire manuals saying exactly how someone would use your code. And once it's in this format and you have a URL for it, the way you can add it to a project, let me just open Julia here. From the package manager, it doesn't even need to be a registered package. This one is, but it doesn't need to be. So you can just copy the GitHub repository and add that, and it will clone that copy of the code, and now you have access to it, like anywhere, basically. So if you have some library code that you use a lot, it's worth putting it in this like package, keeping it separate, updating the code separately, and then just adding it at the end. Okay, any questions about that? Okay, if you have, just email me after the lecture.